Our last method for solving systems of equation is the addition method. It's another algebraic method where you can solve the equations in a sense and get an answer, okay, using algebra. And so to do this addition, basically the idea is you're going to be adding the equations together in order to eliminate a variable. Some people would call this the elimination method instead of addition, but we're going to call it addition. And so we add the equations together. Now the reason you can do this is because there's a property that says you can add the same amount to both sides of an equation and it doesn't change the solutions to the equation. Well, if I add, let's take the bottom one, if I take this equation, I can add the same amount to both sides, two things that are equal. Well, if I add 5 to the right side, I can add something equal to 5 to the left side, and that's equivalent to just adding the same amount to both sides. So you can add equations together using that property. It's a slick, clever variation, but it works. Now the problem in this case is if you add these equations directly, you don't eliminate a variable. Right? If I added these together, 3x minus x, I get 2x. Y and 2y makes 3y. I still have x and y. What we want to do is add them together in such a way that it eliminates a variable completely. One of the variables drops out. I cannot solve an equation unless it has one variable, right? In order, on this substitution method, in order to actually solve for x, we had to get an equation that only had x in it, right? We had to substitute for the y so that we only had x. Here, if I have both x and y, it does me no good. So what we're going to do is we're going to add them when their coefficients, when the coefficients of one of the variables are opposites, okay? So we either want the y's to have opposite coefficients, like 2 and -2, or 17 and -17, whatever it is, so that when we add them together, they zero out. Or we could have the x's have opposite coefficients. And it doesn't matter which variable we choose, completely arbitrary. For the sake of this example, I'm going to choose the x's. And the reason I'm going to choose the x's is because one's already negative. I kind of like that so that I don't have to multiply by a negative to change it. So here, I'm going to take this, I'm going to take the top equation, I'm going to leave it the same. So the top equation will be 3x plus y equals 5. However, the bottom equation here, I'm going to multiply by 3, okay? And in doing that, multiply by 3. In doing that, I'm going to change the -1 to a -3. And you can multiply both sides of an equation by a constant. It's not going to change anything, right? It's not going to change the solutions to that equation. So multiply by 3 here, multiply by 3 here, that gives me 6y. Multiply by 3 here gives me 9. Now this bottom equation is the exact same graph, exact same line, has the exact same solutions as the bottom one here. I've just changed the coefficients by a factor of 3. That's it. But the intersection point won't change. Okay, if I change the coefficients but I don't change the solutions, then I don't change the ordered pairs. The line is still the same. The intersection is still the same. Everything else is still the same. So when I add these two equations together, I'm going to add them term by term to combine like terms. 3x minus 3x is 0x. So those add up to 0. Y plus 6y is 7y. And 5 plus 9 is 14. Okay, so I'm just adding them up by term. And notice 7y equals 14. If I divide out the 7, I get a y value of 2, which is a good thing because it matches the solution, the y value of the solution we found before. But then once I've found that, I still have to go back and solve for x because I only have y, but I need the ordered pair to be a solution. So I can substitute that, and I can put it back into either of the original two equations. It doesn't matter which one I put it back into. So let's put it back into the top one, just because I think the arithmetic works out nicely there. So it's 3x plus 2, the y becomes a 2, equals 5. And if I solve that equation for x, I should get a 1. Let's check it. We'll subtract 2. 3x equals 3. I divide divide out the 3. And sure enough, 3 over 3 is 1. And so again, I can verify that my solution set is the set containing the point 1, 2. All right, so in all 3 cases, I get the exact same solution of 1, 2. And that verifies that I must be doing something right. Okay, so again, the addition method, the main point here is that you add the equations together in such a way that you eliminate a variable. Sometimes you have to multiply the coefficients of one of the equations by a constant in order to get the coefficients to be opposite. Okay. Sometimes you have to multiply both equations. So it could be the case that you have to multiply top and bottom equations by different numbers in order to get those opposites. Typically, we're looking for the least common multiple. So for instance, if this was a 3 and this was a -2 instead of a -1, then the LCM, least common multiple, would be 6. And I have to multiply the top by a 2 and the bottom by a 3 to get them to be opposites. Okay, so you always want them to be opposite values. And to do that, sometimes you have to multiply one equation, sometimes you have to multiply both. It just depends on what the coefficients start out as. Also, one more thing I wanted to mention, almost cut the video there, but I remembered something. Some systems of equations have weird solutions, okay? Not every system will have a single intersection point. And I just want to bring this up briefly. It's not a big part of the homework or a big part of what we're studying, but I think it's important for you to notice that there are situations where 2 lines may not intersect at all, okay? And if that's the case, you may have a situation where you have 2 lines that are parallel. They never intersect. And if that's the case, you'll have no solution. Okay, no solution if you have parallel lines. And the solution set is the empty set. Okay, so you would have an empty solution set. And that can happen if you were to find that that happens, it would occur if both variables were eliminated. Okay, both variables dropped out and the resulting equation was false. So if you had both variables drop out, you had 0 and 0, and then you had another number over here like 14, well, 0 doesn't equal 14, so you have a false equation, which gives you no solution. The other weird situation is you may have 2 completely overlapping lines, 2 copies of the same line. And in that case, I'm running out of space to draw this, so maybe I'll go back over here, get rid of some of this. So if you had 2 copies of the same line, you actually have an infinite number of intersections. Every point on the line is an intersection because they always overlap, they always coincide. So you have infinite or infinitely many solutions. Okay. Now the solution set is a little bit more complicated. I'm not going to worry about dealing with that because you're not really going to see any of these, but I just wanted to point out that this could happen. And the cases in which it happens, if you were to do substitution or addition, what will happen is the variables will drop out again, just like they do for a no solution, but the equation will be true. You might get 0 for both variables and then a 0 on the constant as well, and 0 equals 0 is true. And so you have an infinite solution situation there. So those are just a couple of weird situations that can show up. I don't believe you're going to see any of those, but they can happen. So if by chance you do see one, you'll know how to tackle it. And at least you now know what some of the other options are when solving a system of equations.